Hi, my name is Rodrigo Bini, and I'm a lecturer at La Trobe Rural Health School at La Trobe University in the Bendigo campus. And today I'm talking about the time frequency domain analysis of biological signals. So a little bit of my background: I actually have a bachelor in physical education with honors in Brazil, and I did my master's in human movement science in Brazil as well, working on biomechanics for a very long time actually. And then I did my PhD in sports and exercise science at AUT University in New Zealand. And I have experience especially in sports biomechanics, and I have, as you can see, cycling has been one of the key elements of my research. And obviously that involves, because it involves biomechanical data, it involves the understanding on how signals actually behave over time, and how frequency components of the signal actually change over time as well. In terms of professional practice, I had some experience as a strength and conditioning coaching and actually personal training as well in the very past. Back in the past, I was a research assistant at the Exercise Research Laboratory in Brazil, and a research officer at the Brazilian Institute of Shoe Technology, and that was back almost 6 years ago. Did my postdoc back in Brazil after finishing my PhD in New Zealand, and then I was a lecturer in the School of Physical Education of the Army 2 years ago, and I have been teaching here at La Trobe since October 2016. And I have been doing research most of the time in parallel with my teaching roles. In terms of research, as I said, sports biomechanics has been a key element, and I've been spending a lot of time doing research on the biomechanics of cycling. More recently, I have been doing some studies on running as well, and triathlon especially, and actually the result of our research on cycling has come across this book, which has been published in 2014. So in terms of this particular class, the design that I would like to offer is to cover up to 1 hour theory around signal processing, particularly the time frequency domain of the signal processing, and a little bit of practice, sort of self-guided, and I'll be happy to discuss and ask any questions that you may have on that practice as well. So the main topics that I'll be covering are the time domain analysis, what actually that involves, how does a signal look like on the time domain, what's the difference from time domain to frequency domain, what extra information we get from the frequency domain analysis, and obviously the time frequency domain analysis, which is the critical aim of this particular talk, and a step-by-step scenario, actually more like a self-guided purpose on you looking at frequency domain analysis of different types of signals. So on the time domain, usually we represent the outcome measure in relation to time, or in this case, as you can see, we've got a force measure from a walking gait trial in relation to the samples that we have collected. So it's a force over time if you convert your samples into time based on your sample rate. So you look at the features of or how actually the outcome changes in magnitude over time, which allow you to draw some conclusions around what's the mean value of that graph, what are the peak values, how these force actually change over time as well. So calculating some derivatives of that, but obviously that doesn't give you the full picture. For EMG, which is what you can see here, we have a voltage or raw EMG data, unscaled still, in relation to time, and we've got 5 contractions of different intensity, and obviously you would like to look at some features of that signal. And because the force signal that we showed before is a type of signal that will replicate very often, and it's sort of predictable, you can really derive conclusions in terms of how that signal will actually change over time. So you can sort of predict that in a way. On the other hand, EMG is much more random, which means that within sequences of time durations, you can already derive much of what is going to happen with the EMG signal, right? And the reason for that we'll see shortly, which is when we expand a 1 second block, or in this case a half a second gap on the EMG signal, or if you get a window of half a second of the EMG signal, you see these oscillations or these changes, these random changes on the EMG signal. We actually obviously reflect the way that the central nervous system controls the muscles, which sort of allows the central nervous system to have room for changing coordination often, right? So in other words, EMG is not it's hardly predictable. It's difficult to predict. You have to add many constraints on your simulation if you were to predict that. And the reason for that is that it has a wider range of frequency components embedded on the signal, right? And obviously, if we compare that to the force, and we'll be looking at that, the force and even movement has much constraint, much narrow ranges of frequency components. So in other words, it will not vary too much over time, or if it varies, it will vary within a predictable way, which doesn't happen with EMG. So if you look at the frequency component of EMG, you see that it spreads across a much wider range compared to the force frequency component. And here we've got a power to frequency plot from a muscle during activation, and you can see that you have a wide range of frequencies where you can still see power in the signal, right? So in this case, you can definitely see signal from 0 or a little bit after 0 up to 400, 500 hertz, right? So you have a wide range of frequencies that your signal can be embedded within. And that's very different to what we observe when we look at the force and the and movement as well. But obviously, each type of signal has its own power to frequency distribution, and obviously the what is embedded behind this power to frequency distribution is actually a result of physiological process, which I'll be mentioning later on this talk. So really what we try to get, especially when we look at the frequency component, we would like to understand what is happening on the back end in terms of what is the physiology that is driving this frequency behavior, and obviously how that actually links with what is happening over time. So for example, in terms of the force, what we can see is that, for example, if you look at force and acceleration in parallel, in this case you've got a blue graph which shows the ground reaction force, and you've got a red graph or a red trace which shows you the acceleration measured during gait, right? And what you can see is that you have different, it's the same process, it's the same event, so it's heel strike, but it has different behaviors depending on the outcome that you look at. So in terms of the force, it has a smooth increase, whilst when you look at the acceleration, what you can very much see is a much larger change in acceleration over time. So you can see that it goes up to over 600 and then it goes down and then it goes up back again. So it sort of goes up and down in a random pattern. So the nature of the event that is behind these is pretty much similar, but the outcome is going to be slightly different. So probably to understand what is going on in terms of the mechanisms that is driving this pattern, we would have to look at something different than the time domain principles. Right? So you could look at peak values and you could derive some conclusions based on peak values, but how much of this pattern actually is derived from, and in the case of gait, we have to expect how much of this comes from a cushioning component of the shoe, how much of that actually comes from vibration on the bones. So these sort of things have been explored in terms of trying to look at the signal and trying to determine what is the mechanism behind the way that these graphs are changing over time. So for example, if you get a force graph, and if you separate that force graph into two main elements, so you've got a force graph on the top, and if you just extract from that force graph over time what is greater than 60 Hertz. So you actually high pass your signal, and then you remove everything that is under 6 Hertz of frequency, right? So what you can see, and it's very interesting that when you look at the bottom, you can see that large vibration during heel strike, because we have a gate, again, a ground reaction force, vertical ground reaction force trace over time. And what you can see is very similar to what we observed before for the acceleration, right? So that large vibration in the very early part of the graph, especially the blue graph in the bottom, actually reflects the high frequency components of the impact of the heel on the ground. So in other words, you can really determine the frequency that actually will involve high intensity vibration, and obviously you can assess how much vibration you've got. Right? So by detaching this high frequency component from the main signal, you can look at that and determine how large is that high frequency component, which cannot be done using traditional power frequency spectrum analysis. So the fast Fourier has been there for a very long time, and it's very beneficial because you can see the distribution of the power spectrum of the signal across the various frequencies, which is what we saw before, but it doesn't allow us to determine how actually that changes over time, and doesn't allow us to determine how large are the changes within a particular frequency. You can see that you may have more power within a certain frequency, but you won't be able to tell when that large power actually is happening. But by doing this detachment of this decomposition of the signal into blocks, you can look at that and say, okay, I've got a peak force at 60 Hertz that happens very close to the load response, let's say. In this case, not really load response, but it's probably when you've got the first shock after heel strike, right? So you can determine when on the movement the high frequency actually is happening. If you look at a frequency, obviously you can see that you have a large frequency at very low, a high intensity at very low frequencies. So if you expand that, you see that you have various, and that's for the whole signal. So that this frequency intensity or power to frequency assessment is for the whole signal. So you're looking at very large intensities at very low frequency. Then you've got another peak around 3 Hertz, and then you've got another peak around 4 Hertz. So what you see is that your intensity of is not really showing on the main signal because it's embedded on the overall pattern of the signal. So you really have to detach your frequencies before you actually do a frequency assessment. So in other words, you probably cannot really look at the frequency from the whole signal, trying to determine where is the high intensity, where is the vibration, where is the impact, because that is going to be embedded on the main signal. So it's going to be hidden within the main signal. One of the approaches that have been done actually has been, there were many attempts to address this. This study sort of highlights an interesting approach on that space. So they've tried to determine the effectiveness of different types of material in reducing the high frequency shock during gate, and what they used in the and they stated very clear on the title and it's interesting because they've used the filter bank analysis. So they actually decomposed the signal into various bands, You can see some of the bands here. So they've got a band that is 0 to 10, another band that is 10 to 20, and they go in these windows of 10 Hertz throughout the signal. And that allows them to look at the signal over time for the various bands, right? So you see that, for example, from 20 to 30 Hertz, you've got the largest vibration at a given point in time between, let's say, 200 and 400 milliseconds. So that allows them to look at when actually the vibration was going on. What they did is that they tested different types of materials, and obviously they sort of gauged that based on a traditional force loading rate measure, which is a very traditional time domain assessment of impact during walking and running. And what they observed is that the percentage of the signal above 60 Hertz, which is what you can see on the bottom right graph, actually allows you to differentiate much better the types of materials, particularly when you compare the most compliant material, which is the plastizot, compared to the other types of material in relation to the loading rate. So for the loading rate, although they had a very small sample size, there was a lot of overlap. And particularly if you look at the barefoot on the loading rate, it overlaps quite a lot, especially with the SPANCO and the microcell path. But if you look at the signal assessed above 60 Hertz, you actually can see that difference is a little bit larger. So in other words, you probably can determine much better your vibration by looking at a signal above a certain frequency. So when you look at the signal above this certain frequency, then you can see that, and this intensity frequency plot is for the signal above the 60 Hertz mark, right? So it's a high pass filter of the force above 60 Hertz, and then you can see that you really have a peak that almost getting to 75 Hertz, because the filtering has properties that doesn't really allow it to just chop from 60 onwards. You start filtering a little bit before, so you have a little bit of carryover effect from the lower frequencies. But what you can see is that you really can see large intensity at higher frequencies, right? And that's what we're trying to look at, right? So that sort of overts the benefit of looking at frequency components over time. In this particular case, what we did is that we separated from, and that has been a lot of discussion, and especially when we go back to the EMG space, where we know that the muscle activation measured by surface electromyography, it has a composite of various motor units which are fired in different frequencies, which behave differently because they have different motor inputs. So in other words, you may have a large motor unit and you have a small motor unit, and they may be read in parallel by the same electrodes. So you have a signal that is a composite of different types of motor units, right? And obviously, if you think about fatigue, you tend to expect that over time, you may have changes on how the central nervous system actually chooses which motor units will be selected. So what happens is that we tend to expect that as long as you fatigue, you will have a reduction in your large size motor units because they will fatigue more rapidly, and your small size motor units will endure more because they are resistant to fatigue. So this is the theory, and there's evidence for that in some studies, animal studies, in vivo. But when you go to the practice, okay, so let's try to see from the EMG signal if we can actually really determine or observe a change in the pattern of the signal that allows us to really determine, okay, that's a change that could be related to shifts in priority of recruitment of motor units. What we did in these studies is that we had cyclists coming to the lab and they did a time to exhaustion test. So they had a given workload to accomplish, or actually work rate to sustain. So they cycled at a given power output for as much as they could, right? So really traditional fatigue test. And what we did is that we measured EMG throughout, and then we explored we did an attempt on looking at the EMG signal from different muscles and try to determine how they actually changed over time for various frequencies. So we've broken down this signal from a given muscle into different frequencies to look over time how that actually changes, and that's what we're sort of showing here a little bit. The principle works like that. So you have on the top left side, you've got the low frequencies, and that's why you can see actually the gaps between. So the pattern actually, or the blue lines go up and down, and you can see the up and down pattern of the graph. And then you've got on your bottom right the high frequency. So their analysis allow you to see primarily the differences between frequencies, and obviously in the magnitude, which is what we're interested in, right? We'd like to see how much less activation, how small will be your high frequency from the beginning in relation to the end of the test. Because if you have a reduction in the magnitude of the high frequency from beginning to end, and you have the same magnitude for the low frequency, that would that would confirm the hypothesis, right? We've got some preliminary data here. I'll explain that a little bit more later on. This is just an example of a particular cyclist, and what we did, and you can see 4 different muscles. We know that these different muscles have different fiber types. We know that these different muscles behave differently. They have different roles. They have different anatomical attachments, different muscle volumes. They are completely different, right? And obviously they have different distribution of motor units, right? So for example, if you look at the tibialis anterior, you've got that at 40% of, and that's the bottom left graph, you've got that at 40% of the test, which is the which you can see is at the black bars, and the white bars you've got the same muscle measured at 90%. And what you can see is that you have wave bands. So the wave bands are again our frequencies. So number 1 is the lowest frequency, number 9 is the high frequency, right? So you have a spectrum of frequencies, and you've got intensity or amplitude, or how much activation you've got for each given frequency. So for this particular cyclist, we observed a large increase in the low frequencies when he got close to the end of the exercise, which happened in a way also for the lateral gastrocnemius. You can see a little bit of some increases, but less evident for vastus lateralis and biceps femoris. Obviously, the overall result of this study, which we published, actually showed that the biceps femoris was the most effective for the majority of cyclists. So we had a statistical difference for the biceps femoris. And the reason for that is because the cyclists changed that technique. And they changed that technique by starting activating muscles that are less efficient. So they sort of have this backup scenario where they can engage muscles that are not critical for a certain time or for a given intensity, but when things become too complicated, they start engaging these muscles. And in this case, for this particular cyclist, potentially he started engaging tibialis anterior and lateral gastrocnemius, particularly the low frequency part of these muscles, or maybe the small size motor units. But most of the cyclists actually engage the biceps femoris. Obviously, for what we showed before, what we did is that we used band pass filtering, which is very often used for EMG, but we use that for chunks of frequencies. The other approach, which is fairly similar in terms of the principle is similar, is wavelets. So wavelets then, it's again is a type of filtering that allow you to convert your signal into a different shape within different frequencies. And here you have an example of a wavelet processing of a ground reaction force in 3 different bands. So from 10 to 4 hertz, from 10 to 40 hertz, from 130 to 160 hertz, and from 250 to 280 hertz. You can see obviously that, and that's the issue with wavelets compared to a filter, to a Butterworth filter, is that the wavelets can change the shape of the signal in relation to the original shape. And the reason for that is that every wavelet has a given mother shape. So these are different mother wavelets, different types of wavelets. So each wavelet would suit better a given type of signal. So let's say that I would like to do EMG assessment using a high wave, probably wouldn't work. Some studies have used the Deutsch 4. Others have used, you probably could use the Gaussian or spline for some signals, maybe not for EMG, or the Mexican hat. So it depends on what signal you look like, what's the shape of that signal. You have to pick one given wavelet. And from what I am aware, probably there's no standard across in terms of which wavelet is more suitable for EMG. And I probably can already tell you about other signals, because this is a space where very little research is being done at the moment. So we've got some other options. So the Morley wavelet is one that is often used for EMG, and you've got all the Gaussian wavelets with different derivatives. So again, you have various options on what's going to be the equation behind your processing that will drive your signals. So ideally, you would like to have a wavelet or a filter bank that will allow you to replicate your signal as similar as possible to the original shape, right? So we shouldn't actually change the shape of the signal. If it does, probably you won't be able to have a good representation over time. So if you'd like to look at the frequencies over time, you wouldn't be able to represent that properly if your mother wavelet doesn't really reflect your original signal. In terms of frequency band, what you can see is that by using filters, regular filters like the Butterworth filter especially, you've got a benefit that once you filter your signal, your outcome usually reproduces fairly well what the original signal looked like. And here you've got a good example, again, our ground reaction force from the walking trial, and then we've got there from like a low pass from 0 to 10 hertz. So just a low frequency component, and you can observe that the shape of the ground reaction force after filtering really looks like the original signal. Obviously, you have removed the high frequency component, which now is being shown on the bottom panel, which is the green line. So you've got anything greater than 10 hertz is being shown on the bottom. So you've got that vibration when the heel actually hits the ground presented in the bottom. So for example, if you do a walking gate trial and you filter your signals over 10 hertz, you're really removing high frequency components from the signal. They are natural to the signal. So in other words, you're removing critical information from your signal. So you're removing parts of the signal that should belong to the signal, right? And that has been a space where there's not a lot of discussion in terms, or actually the discussion that I have seen is more around filtering the less possible, because people have become aware that over time the equipment has improved, right? So we have better technology today than we had 20 years in the past. In the past, our technology was okay, so we had to filter a lot our signals because there was noise from the hardware, right? These days, we don't really have to worry too much about it. We have to expect that our hardware will be of high quality. So the signal that will be recording on the computer has to mimic what has been happening in real life, right? So we have to make that assumption. And the reason for that is because we have been removing important components of the signal in lots of studies in the past. And this is a good example. So anytime you filter your signal, you will remove some parts of that really belong to the signal. In the case of the force data, you're removing the impact part of that, which depends on what you're looking at. It's going to be critical. So if you're looking at inverse dynamics or any type of modeling that would require force to be as similar as possible to the original to match with acceleration components, you just adding errors to your data. So you really should be careful whenever you filter your signals and filter as less possible. So the least possible filtering should be applied to any type of signal, unless you have a really good reason on why filtering the signal, and that has to be aligned with poor hardware or hardware that are adding noise to the signal. So here we've got a good example. We have a tracking of a sacrum marker on the vertical axis, so two-dimensional filming. We stick the marker on the sacrum and we are tracking that marker when the person is doing a squat. So on the top panel, what you can see is that is actually the tracking, and you can see there is some noise from actually tracking the marker, which happens especially on two-dimensional video-related tracking of displacement. That happens, and we are aware of that, right? And what we have been doing often was to low-pass filter that signal to sort of smooth a little bit the pattern of that signal. And you can see that it really does. So some of the noise has been removed. There's still a little bit of noise over 6 Hertz, and the resulting the component of the signal that has been removed is in the bottom. So you can see very clear that there is a high frequency component from the issue on trying to find the centroid of the marker, which is really what happens when you're trying to do movement analysis. You have a marker on the screen, you try to hit the centroid of the circle, but you never get to the center. So you really have a high frequency from attempting to find the center of that marker. But that is a case for a single camera, right? These days we are really talking about multiple cameras, so the error from one camera is mitigated by the other camera. So in the end of the day, your markers are much more clean than they were before. So they are of much more larger quality. The data is much better than it was before. So why filtering? The question is then, why doing low pass filtering if your data is coming in of low quality with reduced noise? So that is a question that people have been starting to ask again, in order to try to ensure that the data that is going into that is going to be used on your analysis is less affected by interim processing. Here we've got an example of an accelerometer data. So the accelerometer is still probably the data that is much noisier than the examples that we showed before. Probably EMG has, it could have some noise embedded on that, but obviously accelerometers, they are noisy in nature, especially because the attachment of the accelerometer, they are very sensitive, and the attachment of the accelerometer to the skin is usually difficult, because if you don't have that properly attached to the skin and especially bone structures, you could have soft tissue influence on your accelerometer data, which is probably what we can see here. We've got an accelerometer that we attempted to strap, to attach to the sacrum of the person whilst doing a vertical jump. Our accelerometer was limited to 2G in terms of vibration, so we couldn't actually read anything beyond 2G, and that's why you see that there is a sort of is capping at 2G, so there is a cap in some parts of the blue signal on top. When we sort of break down the components in terms of frequencies, what we can see is that a lot of our noise actually is beyond 5 Hertz. So when you filter the accelerometer data lower than 5 Hertz, what you can see is that you have again a much smoother pattern. You remove a lot of that noise that is coming along at the other band, so 10 to 15, and particularly 5 to 10 Hertz. You have a large magnitude on 5 to 10 Hertz, which means that you've got a lot of vibration being read on the accelerometer from 5 to 10 Hertz. And that's probably, and if you look over time, that is probably when the person landed, because that graph is from a counter movement jump. So you have at sample 290, so the first dot point that we added that, we have 9 as the acceleration, which is a standstill position. Then we have a reduction in acceleration in frame 385, which is the counter movement part of the jump. Then we've got a takeoff at 406. And then after that, we've got this large vibration, which is very much when the accelerometer, when the person is airborne. So the accelerometer is vibrating from the takeoff, and obviously when landing. We've got a lot of vibration when landing, which is when impact actually happens. So our accelerometer is certainly reading two things in combination. One is the noise from the attachment of the hardware with the skin, and the other is a vibration from impacts during landing, from the impact of landing. So you really are looking at two things in parallel. So if you would like to look at the jump itself, you could use the low band of the accelerometer filtered data, which clearly shows you a flight time, or shows you fairly well a flight time. And then you have to look at the vibration and separate and try to see how much of that vibration comes from the impact itself, and how much of that vibration comes from a soft tissue noise from the attachment of the accelerometer. So accelerometers are good in terms of example to show you the this influence from various components. In terms of force plates, we did pretty much the same using a force plate. So again, counter movement jump. First dot point in the top panel, we've got a person standing still, frame 8241, so standing still. Then you've got a reduction in the force during the counter movement part of the jump. You've got a peak force before taking off, which is when the person is actually building up a momentum to get off the ground. You've got a flight time when you have no force readings, and you've got your landing, which is your peak force after the flight time, right? So traditional or very often observed force over time graph for a vertical jump, right? What you can see then is again our components. We've broken down, and we used different bands in this case because our force plate was recording a much higher frequency, so we could expand a little bit more. In the previous example, the accelerometer was recording at 50 Hertz, which is pretty low sample rate for vibration assessment, but the force plate gave us a much better resolution. And what you can see, and it's very interesting, you can probably see most of the signal between 0 and 20 Hertz. It's chopping parts of the signal, but you can see the pattern, especially the peak force before flight time and the peak force during land. They are all represented on the low frequency spectrum of the data. But when you look at the other frequency components, what you can see is that your high frequency is really happening between 20 to 40 and between 40 to 60 Hertz. That's when your peak force on the high frequency band is going on, in particular between 20 to 40. You've got a peak force of almost 400 newtons going through your body at a frequency of 20 to 40 Hertz, right? During landing. And that's all landing. You can already see, that's nothing going on, largely going on during takeoff at high frequency. It's all about the landing. So the landing really is applying a large chunk or a large amount of vibration to your body at large intensity. So large intensity, high frequency, which depending on what you're going to do with this information could be important. So let's say that you're thinking about injury prevention. You would like to reduce the likelihood of someone developing an overuse related injury, and you have data showing that high frequency vibrations could be detrimental to an injury perspective. So this could be an information that you could use to try to teach people how to land better, or how to land in a way that you could reduce the high frequency component of their landing, right? Another thing that can be explored in terms of the time frequency domain analysis is the postural balance, or balance measured by the center of pressure. So here we've got a center of pressure trace on the anterior, posterior, and medial lateral components over time, and then you've got the filtered elements of that. So you've got a low frequency component of that and a high frequency component of that. I'll mention a little bit later on, there are studies relating different components of the central pressure with controls from different sensory systems. So in terms of the physiology behind the time frequency domain, so in terms of the EMG, obviously, as I said before, it has been linked to the recruitment of motor units. So it has been associated with high and low frequency bands being related to large and small size motor units in terms of activation. There are studies, in particular this study from Wakeley and others, that they have associated the high and low frequency components with and these particular bands with activation of large and small size motor units. So they have proposed that these ranges could allow you to see the high and low frequency bands, that could allow you to see priority of activation of large and small size motor units. From studies that we have done, you probably can get good sensitivity when you have extremes. So when you have the person undertaking large amounts of going through a very going close to exhaustion, right? So that's probably the best way to describe. When you have your participant or your client going close to exhaustion, that's when EMG will be sensitive to these changes. Anything sort of mild fatigue, some studies showed differences. We couldn't find, or most studies couldn't find a difference. So it's more difficult to observe differences in recruitment when you have mild or moderate level of fatigue. So you really have to, you're really talking about large amounts of fatigue to be able to observe on a surface EMG signal that is really affecting the recruitment of motor units. And obviously the reason is around the limitations of EMG, right? So you have a certain area that you can actually capture the signal that is a lot smaller than the muscle size in most cases. So if you think about a vastus lateralis, your capturing area is much smaller than the volume of the muscle. You have a depth problem, which means that if your small size motor units are in the bottom of the muscle, they have a filtering effect before getting to the electrodes, and they will be filtered off from your signal sometimes, especially if they are too far off. You've got obviously the subcutaneous tissue, which can remove again the low frequency, can reduce even more the low frequency components of your signal, and can lower the frequency of your high frequency signal. So your large motor units may get into the low frequency band because you may have a thicker subcutaneous tissue. So these are the limitations from EMG in general. It doesn't matter if you look at time frequency or if you look at just time domain or just frequency domain. It's going to happen anytime you use EMG, right? We are aware of that, but we still believe that EMG has valuable information, and that this is one of the scenarios. In terms of the central pressure, the engagement of sensory systems or different engagement of sensory systems has been proposed. So we are doing a few, probably a couple of studies looking at that in different scenarios. And obviously would like to see if these low and medium frequencies could be affected by the additional removal of visual control, somatosensorial and vestibular systems, and the high frequency band being associated with proprioception. So there are possibilities around that in terms of trying to assess if really this analysis is sensitive enough to allow us to really determine if you have a system that is actually taking over the larger portion of the role when you do certain things, let's say an intervention, or when you have people injured, recovering from an injury or with a given disease. In terms of kinematics, what I've showed some examples before, but what you probably can see is around the use of these filtering mechanisms to remove noise from tracking of markers. And obviously here we're talking about filtering noise. We're not talking about extracting components from the kinematic data. And that's because I think there is still a little bit of discussion around how much we should filter or not. Some people are saying, no, we shouldn't filter anything. Some people are saying, yes, we have to filter because we still have some noise going on. In terms of ground reaction force, especially the vertical ground reaction force, and the link is with impact, obviously. But again, it's expected that 95% of the signal energy or the amplitude of the signal should be below 10 Hertz, right? So in other words, you are to expect that you would have 5% of your signal above 10 Hertz. And that's important because you have a really narrow band to detect the changes in impact in the higher spectrum. So that gives you limited room. And again, you're probably talking about extremes again. So scenarios where you have large changes in the movement pattern that really determine difference in terms of the impact. So in terms of practice, what I can offer to you is to give you some data and some codes that we have developed that will allow you to separate our data into frequency components using two main approaches, a frequency band analysis and a wavelets analysis. And you can probably compare the results. We have some MATLAB codes that you can have access on this Google Drive folder. This will allow you to do the comparison. I'm happy to provide any clarifications if you have, and to show you especially some of the codes and how they work. Obviously, you have to have a little bit of minimum experience on MATLAB to upload the data, select the variables they would like to, and calculate the outcomes in terms of looking at the amplitude or the intensity of the signal within the given bands. I'd like to thank the opportunity to talk to you. Here's just a beautiful image that we've got from the city center of Bendigo here in central Victoria, and that's my email. If you have any questions, I'm happy to touch base with you and to clarify any queries. Otherwise, enjoy the rest of your day or evening, and see you shortly.